Hi, I'm Tom Chen. I have the pleasure of working with two students this summer. Eislym is on her last semester here at IMC, and she wants to, and she's currently learning sign language, so she will be adding that onto English and Spanish that she currently also speaks. Eislym is also a STEM scholar. Inci is an early college student on her last year, and she also speaks Turkish. She hopes to go to med school. So without further ado, I'll give the presentation to them.
Hi, everyone. We hope everyone's doing well.
Okay, we got it right here. Yeah. So my name is Eislym.
And I'm Inci, and we tried to find the thermodynamic properties of two common pH indicators, thymolphthalein and phenolphthalein. Phenolphthalein actually has a lot of good research supporting a lot of its properties. However, there is a lack of research regarding its thermodynamic value, its heat of reaction, and its entropy. And thymolphthalein just lacks general research altogether, and they are common chemicals used in the chemical research industry, so we wanted to provide these values for future research.
And here you can see just a general outline of how we're going to touch on the, each indicator. We're first going to go with phenolphthalein. This is a common pH indicator. It's mostly used in acid-base titrations as it changes color in a pH of somewhere between 9.5, 9.8. It was used before as an laxative, commonly known as X-Lax, although it was banned by the FDA in 1999, mainly because of research that came up in mice models done by the FDA and the National Institute of Cancer. And they found out that there might be some carcinogenic properties to it. So now it is removed as a laxative and mostly used in the Kessel Major test. You can see it in the bottom picture. And this mainly works to identify any type of substances that may contain blood. So the ways that it works is that you add hydrogen peroxide to a acidic solution, and it's gonna oxidize the hemoglobin present in the blood. And then phenolphthalein, which is a smaller container, it's added to that, and that's gonna reduce the oxidized hemoglobin, and it's gonna turn to a lighter pink. Depends on how much it is present, it's gonna go to a darker pink. And that is also the main color of the indicator. You can see in here in the chemistry of it, it has two main structures. The one to the bottom left, it's going to be the colorless. That is its main structure. It's anywhere when the pH is below 8. Then when the pH is higher, more acidic solution, it's going to turn to a color structure. And this is mainly due to a structure change and a gain of a -2 charge. It's going to increase the solubility in its interaction with water. And in here you can also see the pKa, it's going to be around 9.7, very standard for this type of pH indicator. And the molar absorptivity, which is just how much light it can absorb, it's going to be around 30,000.
So like phenolphthalein, thymolphthalein is a weak acid, and it turns slight blue at around pH 9.3, and it increases as the pH of the solution increases. So right there, you see what thymolphthalein would look like in a solution at around 10.5 pH. Thymolphthalein is commonly used in laxatives. Unlike phenolphthalein, it has not been banned yet. However, there has been a shift toward using fiber-based laxatives instead of thymolphthalein-based laxative because it has been linked to side effects such as vomiting and rectal bleeding. It has also, in rats, been correlated to cancer, colorectal cancer. Again, the FDA has not banned thymolphthalein quite yet. Another use of thymolphthalein is its use in blue disappearing inks because it neutralizes so easily. It can go from colored to colorless very easily, meaning it's used in a lot of disappearant inks. Now, as I said, thymolphthalein turns blue in pH above 9.3. How does this work? Well, it's a weak acid, so it loses two hydrogen ions. And this structural change gives it a slight -2 charge, and it is perceived by the human eye as blue. Now, I also mentioned that it's used in ink. Why? Well, it neutralizes so easily. Thymolphthalein is a weak acid, so it has a strong conjugate base. It hates being negative. So carbon dioxide, molecules like carbon dioxide from the air and surrounding molecules can neutralize it very easily and make it colorless again. Now, we talk a lot about what our molecules are, but we haven't exactly gotten to what we're doing and how we're doing this. Now, we have this beautiful equation right here. It's called the Van 't Hoff equation. This is going to give us, help us relate our data to what we're trying to find, the heat of reaction right there and the entropy of the reaction. But this isn't a common formula. We don't really know where it comes from. Well, it comes from these very common three formulas, the equilibrium constant and the two Gibbs free energy formulas. We can relate them to each other, and with just a little bit of manipulation, we get this equation.
Yep. And that equation that you saw at the bottom, as you explained, it's going to be the Van Hoff equation. This is commonly used to plot this graph right here, which is the Van Hoff plot. It is very used to relate the inverse of the temperature against the natural log of the equilibrium constant. And it's quite used to be able to find thermodynamic properties of any indicator. For us, it was very useful because, as you can see here, you have the enthalpy and entropy both present in it. So by relating it to the equation of the line, as it is in exactly the same format, we can easily solve for enthalpy and entropy. And as you can see here, we use R, which is the gas constant, and this is the value that we use for that, mainly because it's the most useful in the units that it contains. For the how we did this, we actually did several different buffers at different pHs, going from a more neutral pH to a high pH, mainly because, again, our pH indicators both turn color somewhere around 9 to 10. And we also first dissolve each of our indicators, because they were in a solid state, into ethanol and then deionized water. We did find a little bit of solubility problems with both of them, mainly with the thymolphthalein. But still, it was possible to be mostly dissolved. Then we use this to run it through a UV-Vis and get the lambda max. I'm going to show you just after how we got that. And from there, we can obtain the molar absorptivity, which is just how much light it can absorb. We did this under high pH 11.5. And then at the end, it was all run through run UV-Vis. But that one was done in changing temperatures, just because to be able to obtain thermodynamic values, you do need different temperatures. It cannot be done just at one single temperature. So for phenolphthalein, the absorption that we did, that was the first run. It gave us that graph that you see right there. The most important item in it is going to be the absorption that we got, which is this one right here. This can be used in this equation, which is commonly known as the Beer-Lambert law, which relate the absorption to the molar absorptivity and the concentration of the compound. So we just replace the absorption and the concentration as they were both known, and solve for the molar absorptivity, which is then used to find the total concentration of the buffer. Then this one we got, for mine in particular, I got 8,000, which is about a quarter of what is expected. And so for any calculations from now on, we use the literature value. just a small note in here, it's likely due to the solubility issue that we found. Probably had a higher concentration than it was supposed to have. So that may cause the molar sensitivity to be this low. And also it shows two peaks. The first one that it is there is actually below 400, which is not we cannot be seen by the human eye. So we didn't take that one into account. It's just 553, which is it's very in agreement with literature data.
So for thymolphthalein, we found the max wavelength, the lambda max, to be 594 nanometers. This is consistent with literature. Literature cites it to be anywhere from 592 to 598 nanometers. So that is accurate. However, I face the same issue as Eislym did with phenolphthalein, because as you can see, these two molar absorptivities are nowhere close to each other. We got around 2,200, and the literature value is about 38,000. Now, what might have caused this? I also faced the same issues as Eislym did with solubility. We thought the solubility was a lot higher, so we might have thought it was 1 molar, but in reality, because of the solubility issue, it could have been 0.1 molar. This would have affected the calculated molar absorptivity. Another problem that might have happened is that this measurement was done over the course of an hour. That is a long time for thymolphthalein to neutralize with carbon dioxide. And you need color to measure absorbance. So if it had neutralized, you would have lost the color. Thus, the absorbance would have been lower, and the molar absorptivity would have also been lower.
Yeah, and again, for the last run, which is the one that is going to give us the thermodynamic values, this is the setup that we used. We did a range between 20 and 60 Celsius, and the most important in here is going to be the whole temperature. We wanted to have a whole temperature that was long enough for the temperature to get even throughout the 8 cell cuvette, as you can see it here. But since it only holds 100 microliters, it didn't need to be like 10 minutes or so. 3 minutes should be just fine. And we did run a reverse scan on it, which it was from 60 to 20, just to make sure that the experiment was reproducible, and that it could be reversed. And in here, cell 1 and 8 hold a blank, which is the ionized water. 2 and 3 hold thymolphthalein. 4 and 5, it's phenolphthalein, which is my compound. And 6 and 7 will be 3-nitrophenol. It's a different indicator. And here, for phenolphthalein, the Hoff Plot is as shown there. The most important items in here is that we got our, or the enthalpy to be positive, which would be characteristic of an endothermic reaction, while the entropy was negative, which just shows that the entropy in the system is decreasing and characteristic of non-spontaneous reaction. Both of these go against with how it would behave naturally, mostly. And this can be due either to the solubility issue that we found again, and also to the fact that phenolphthalein does have a third structure in which at higher pH, somewhere between 12 and 13, it's going to go back to colorless. And as the pH used was 11.5, we're not so sure that all the molecules were in that color form. So it might also show up in here, changing the enthalpy into a more positive when it should be more negative.
Let's take a look at thymolphthalein's Van 't Hoff plot. We can see that the slopes and the B values are relatively close to each other. This is good. This means that our scans had high reproducibility. And when we take a look at the delta H and the delta S values, heat of reaction and entropy, we can see that thymolphthalein, the reaction of deprotonation of thymolphthalein, is exothermic, and it has a negative S value. What does this mean? Well, this makes sense because deprotonation is an exothermic reaction, so it should, in theory, be negative. But why is delta S negative? Well, thymolphthalein gets more and more soluble as it deprotonates, so this could explain the delta S value being negative, it also forms multiple carbon-oxygen double bonds, which could contribute to the negative delta S value as well.
And in here, just a couple suggestions that we have for future experiments on either of these indicators. We would mention the solubility issues. A little more focus needs to be done on them, mainly to reduce the possibility of some of it not being fully dissolved, and again, causing it to be more negative or positive, the enthalpy and entropy, which would then cause a reaction, which is something that we got, would cause delta G to be more positive, which is characteristic of an spontaneous, instantaneous reaction. Again, this is not according to what it should be done. We're not able to spot exactly in which step the problem was, but we do have suspicion that it was because of the solubility issue. Also, for thymolphthalein in particular, more emphasis needs to be done in removing the carbon dioxide that can be present in either air in the acyl cuvette or in the deionized water used. Again, as getting make sure everything is fully clean. Again, if it isn't fully colored as it should be, the absorbance is gonna vary and not be the real value. And this can be done by using a valuable nitrogen in the experiment. And then for phenolphthalein, I touched on it a little bit. We don't want to use such a polar buffer, mainly because it's going to push it to that third structure. And although technically or most commonly used, it's like a high pH is usually preferable just because it would push all the equilibrium toward that color structure. For phenolphthalein in particular, using such a high pH would cause it to the third structure, which is back to colorless, and that's not the goal.
So what do we conclude from this? Well, to start off, thymolphthalein and phenolphthalein are extremely similar structured compounds. The one up top is phenolphthalein, the charged version of phenolphthalein, and the one at the bottom is charged thymolphthalein. Now, we can see from the values that we got is phenolphthalein was endothermic. Well, there may be some fault to that. It was endothermic, and thymolphthaleine's reaction was exothermic. And we can see that the delta S values were both negative. But there is about 100 joules per mol K difference between the two delta S values. Now, why? Well, we can kind of relate this to the solubility issue again with thymolphthalein and phenolphthalein. Thymolphthalein is extremely insoluble when it's neutral, and then it becomes slightly more soluble, so more soluble, let's say. Phenolphthalein is somewhat soluble, and it becomes more soluble. So the solubility difference between the two ions of the compound is drastically different. We think this explains the difference between the entropy values. They should be both negative, but we expected them to be kind of close to each other. There is 100 difference, but we think that the net difference between the solubility kind of explains this. Also, because phenolphthalein is more soluble when it's charged, the surrounding water molecules, it would interact with the surrounding water molecules more, so this also explains phenolphthaleine's negative entropy value.
Yeah, and we just want to thank a couple groups here. First, the MC Honors Scholars program for allowing us to take this course. The STEM Scholar in LA College, because both of us participate in both of them, and just because of that, we are able to do this experiment. To the CBS department here at Germantown, the laboratory staff, for supporting us in the UV-Vis, in the lab, and all the problems that we encountered throughout the way.
We would also like to thank you guys
Yes.
for listening, and we would love to open up the floor to questions if anyone has any.